Okay, so I've copied all of the homeworks in here. So if you guys have some questions, and I even put in some of the notes in between, like the relevant notes. So I spent a little time on this for you guys. And this one, I'm so sad. You saw it, and you saw it. They came to my office hours on Wednesday. I had prepared this little solution to number 7, this really tough problem. It's a tough one, yeah, and I love it. It's a great homework problem. I'll tell you why in a minute. And I had it all perfect. Perfect, like little equations revealed and everything, and they saw it in my office. I get in there this morning, it's gone. That slide is gone. All that work. I mean, it took me, an hour, but still, I hate losing work. I hate, you're doing a report, and a computer glitches, and you got, I can't open the file. It's been corrupted, and I don't want to throw it out the window. Ron Swanson, the computer in a dumpster, So, I mean, it's just so so I'm really sad about this morning, but we'll talk about that problem. So, which ones do y'all want to talk about? Oh, time out. I did extend 12. I made it unlimited attempts, so you can go back to 12 and make sure you get the credit for those last 5 problems.
Okay.
Okay, so y'all are good on that. Okay, back to you.
On Wednesday, we said it was 60. There was just no world where I was getting that answer.
Okay, 22.
I thought it was
I'm trying to find it.
A unit switching, but it's not.
I need to get rid of the animations on those. 22. This one.
Yeah, I thought you were just supposed to switch it from centimeters to seconds to meter or hour. Like, I didn't know. I don't know what's happening.
Yeah, okay, so we look at the diffusion equation, and so this is one of those proportionality ones. And so the distance that it diffuses is you have 2 possibilities. I think that's in the previous slide, or close to the previous slide. All the animations. I'm going to have to stop those. Diffusion. Maybe it's afterwards, sorry. Here we go. Okay, these 2 equations here. So this one, and I even got the little problem. Look, I've got it right there in the notes. Okay, so linear diffusion, like in a pipe. So if you have, I'm trying to think of an example. You've got something that, I don't know, leaks into a pipe, right? I don't know, but it diffuses along the like the length of the pipe. That's a linear distance. Does that make sense? Okay, versus in space in 3 dimensions. And notice that this one is multiplied by 3, and you get the 6 there. So this is in all directions, 3-dimensional diffusion versus linear diffusion. Okay. So we don't have anything in this problem that says it would be linear diffusion. So it's not this top one, it's this equation right here that goes in there. Now, you see this is the distance, or the radius it travels. And it's square root dependence upon the diffusion coefficient and time. So what we would say is that this distance is proportional to square root of time. So this is the skill I want you to have. If we know this proportionality, let me see if I can erase these guys. No. If we know this proportionality, so I want to do it up here. So R is proportional to the square root of time. First of all, do you see that in this equation? So you look at R, we don't know anything about the diffusion coefficient, but we know time. Okay, so what we're writing up is we're not writing out the whole equation. We're writing out just the time piece. So on the left is R, which is what we want to know something about. And on the right is what we have. We have the time. But in this equation, it's the square root of time. So you have to keep the square root. Does everybody follow me? How you get the proportionalities out of an equation. Does that make sense?
I would never do that.
So this is why I'm teaching it. Yeah, that's why I'm teaching it now. This is the skill you need to pull out of this course, if nothing else. We use this type of analysis all the time. And we do it a lot with the flow equation. We do it with the diffusion equation. So you need to be able to look at an equation and see what the dependency is. What I mean by dependency, is it just time, or is it time to the 1/2 power, like this? Or is it time cubed? Remember we were doing partition functions and we had the translational partition function and it was temperature to the 5/2 power or 5/3, I can't remember what it was, or 3/5. It had a really weird exponent. You've got to take that exponent dependency into consideration. Because if you double something, is the result just doubled, or maybe it's to the 4th power? So you got to take into account the dependency. And so this is saying it's a dependency on time. So what we can do whenever we have this is we can say, I'm going to do 2's and 1's, 2's on tops, 1's on bottoms, R2 over R1. Oops. And then we take the square root T2. Gosh, I'm saying things and I'm writing different things. Okay. So you can always turn this proportionality relationship into an equation by adding the 2's and 1's. So we have situation 1 and situation 2. And if we take that ratio, all the things that don't change have canceled. Like even if we use the full equation, the 6's would cancel when we did the ratio. The diffusion coefficient would cancel when we did the ratio. So the only thing left is what's changed. You did this in your Chem 2 class with the ideal gas law. You had PV equals nRT, situation 1, situation 2. What happens when the volume changes and the pressure changes? How did the temperature and the number of moles or whatever it is that you wanted to look at? So you've been doing this your whole career, but I really want to emphasize it because in this class we have a lot of weird things like square roots, 4th powers, and so on. So this is the equation that we have, and so this is rearranged. We move the R1 over here to the right, and we have this T1 over T2 over T1 to the 1/2 power. So T2 is 3,600 seconds, right? 1 hour is 60 times 60 seconds, right? So seconds per minute and minutes per hour. So that's 3,600 seconds. And then the original situation was 1 second, and the original distance was 1 centimeter. So we end up getting 60 centimeters out. Do you see how the square root dependence is important? Because if you didn't keep that, then it would have traveled, you would have said it traveled 3,600 centimeters. And instead of traveling 3,600 centimeters, it only traveled 60. Yeah. 3,600, yeah. Yeah, there you go. Yeah, that's right. Okay, so that's right. That's where your 36 came from, because you didn't take into account the 1/2 power. And that's why I teach this skill, because not everything's linear. In fact, a lot of things are not linear. If you come out of this class and you can do that, then I've done a great thing, because this is a skill that will really help you. Yeah. So, morning. You need to watch the video of what I just did. Okay, because it's an important piece. Yeah, so we just did number 22 on, was that number 13 homework or 12 homework? Yeah, the end of 12. I opened 12 up to where you have unlimited attempts, so you can go back and get those points on those last 5. Mm-hmm. Okay, next question. And notice that while you're thinking, this is the diffusion distance over time. Notice it's always a curve, right? This RMS value is just to represent, the curve. So it might be, it's kind of like the average. It might be right here, but then after 1,000 seconds, it's right here. And then after 3,000 seconds, it's right here. And then after 10,000 seconds, it's right here. So it's that single number that's representing the curve. So it's moving with the curve. But you notice how, if you got a source, I like to think of this like a candle, and this is the diffusion of the smell. So right here at 0, You've got your nice candle. See my candle? Look at that. Okay. And so the vanilla or creme brulee, which I really like, okay, is spreading out through the room. You know, when you light it, it's right here on the red right away. You know, close to the candle, you can smell it. A different place in the room, you don't smell it. But over time, that creme brulee will diffuse throughout the room, and that's very nice, especially if it's a good smell like that. Anything with cinnamon? No. I like cinnamon with sugar, but I don't like cinnamon by itself. Okay, your questions. Creme brulee, probably, or vanilla. I like vanilla. Man, it's good. Can't get enough of vanilla.
The phrase have collision symbols and stuff. It wasn't a question on the homework, but it was in the PowerPoint, and I don't really grasp that.
Okay.
Like how a question would.
If it's not in the homeworks, then I'm not going to emphasize it on the test. Okay. So you can look at the homeworks and really study those and know those well. Okay, so if it wasn't something like I really didn't include the activity coefficients in the homeworks. Okay, so that means we're not going to be doing those. Okay, maybe ionic strength. Let's calculate ionic strength. I'll have an ionic strength problem on there, and that's pretty straightforward. You got to take the ions and their charges, square those charges, and then just because that's going to be something that you might need to calculate. Nothing else, you'll see it and it's integrated, but you've already seen it. You're already going past that.
I feel like I'm just a little confused about what this test is going to be like, because in the past too, we've had like a figure that we're pulling.
Right. This is more computation and vocabulary.
So
Yeah.
do I just do equations, like just math?
Yeah, just computations, like all of these little flow computations and stuff like that. I mean, it's just calculating these numbers. Now, the vocabulary stuff is understanding like these equations with the, most probable, average, and root mean squared, and just having a feel for this slide right here, and put these on your note card, but being able to look at those and say which one of these is larger than the other, right? And so you've got 2, you've got 8 over pi, and you've got 3. Well, 8 over pi is around 2.5. So you see the most probable is 2, the average is 2.5, and the RMS is 3. So RMS, and you can see it on this chart here, the root mean squared velocity is higher than the average velocity, which is higher than the most probable velocity, because this is not a symmetric distribution. It's not a Gaussian curve. It's skewed to the right. And so we have these different values, and we'd like to use the RMS values when we have a skewed distribution like this, because it represents those higher values that you have. So, we've got some of these velocities that are really pretty high. And so the RMS value represents a little bit more of the reality that you're going to have some really fast molecules in it. The most probable is just the top of the peak, the highest point. But notice all of these. So let's do the proportionality too. So I want to say the velocity is proportional. And how would I write mass? How would I write the mass dependence of velocity? Yeah, so 1 over the square root of m. Yeah, or you could write it like you said, it could be proportional to the square root of 1 over m. Either one of those, they're equivalent. Yeah. So if I had 2 masses, like I had a helium and argon, right? I would do the 1s and 2s. And so I would say, let's just do helium here and argon. And we're going to make an equality now. So I want to know the masses of those two. So I've got the square root here, and I've got a fraction, and I've got 2 masses. And here's the trick. Which one's helium? Which one's argon? Yeah, so if you look up here, this velocity, mass is in the bottom for this velocity. So if helium's on top, this is helium down here, and this is argon on bottom, so the top one would be argon. And so there's your equation. If you had the two masses and you had the two velocities, let's say you had one velocity and two masses, and you could calculate this. Let's say we had a velocity meter and we measured the two velocities and we had one mass. So you just do the algebra and you could say the mass of the helium. We're gonna square both sides, so this is gonna become squared. We're gonna get rid of that square root. We're gonna bring helium over here. Uh-oh, where's my eraser? I've lost the ability to erase. I don't know why. So and this will be, since this is on bottom on the left, when it moves to the right, it'll be on top. Argon on top, helium on bottom, and this is squared. Do you follow the algebra on that? So I got rid of the square root by squaring both sides. I moved helium to the left, and I moved this fraction over to the right. And that's what I end up with. And so that would be if I had the mass of argon and I had the ratio of their velocities somehow, I don't know. But given in the problem, I would take the ratio, square it, multiply by the mass of argon, and then I have the molar mass of helium. Say again? Yeah, so that was for this one up here. I started with this relationship, and then I was able to do all of that other thing. Yeah. And you could do the same with temperature. So it's it's proportional. So velocity is proportional to the square root of temperature. So if I multiplied the temperature by 4, so I went up from, say, 100 Kelvin to 400 Kelvin. That's a huge amount. But I went up by a factor of 4. It only doubles. The velocity only doubles because it's the square root of that. Square root of that multiple of 4 gives you a multiple of 2. So I would only have doubled the velocity, even though I multiplied the temperature by 4. So that's the skill behind the homework.
So if I wanted T for that first one, would it be proportional to the square root of just the T?
Yeah, so if you only had, like, you're reading a problem and it says, oh, helium goes this fast at room temperature. How fast does helium go at 300 degrees?
Yeah.
Or 500 degrees,
yeah.
Or Kelvin, and so then you say, well, I'm only changing temperature. So you could write this relationship. V is proportional to square root of T. Then you could do your 2's and 1's. So V2 over V1 is the square root of T2 over T1. And so I'll just write that out here.
But
so
it would only be 2 by itself. Like I don't need the 2 R because R is a constant, right?
Yeah, that's right. So those and so this would be T2 and T1. Notice that the 2 is on top and the 1 is on bottom, whereas down here they were opposite because they were inversely proportional. So helium here, but here it's 2 straight across because you see this, there's no 1 over. Yeah, the 1 overs catch you. That's where a lot of people mess this up. Let's, if we were to take this and divide it by, I'll say MP1 and new MP2, and we have the square root of 3R1T1 over M1. Oh, 2's. I should put 2's. Sorry. 2, 2, 2, and 1, 1, 1. This is a 2 here. Notice the 2 can't change. It's a constant, so it cancels. R cancels because it's a constant. And so I've got T1 over T2 or M1. I could bring this M2 on top. Basically, it's the same algebra. But if none of that other stuff changes, it would cancel if you did the whole equation. So you just need to do the proportionality, and then you can set up your 1s and 2s and make it an equal sign. If two things change at once, like say we change temperature and mass, then you would just keep both of those. You would say nu 2 over nu 1 is equal to the square root, and it would be m1 over m2. That's the mass dependency. Notice the 1s and 2s are swapped, top and bottom. And then T2 over T1. So those are straight across. And so there, if you change two things at once, the R's have canceled, the 2 or 3 or 8 over pi have canceled, and you just have the masses and the temperatures left. But notice how you got to pay attention. Is it directly proportional across, or is it inversely proportional, 1 over? So that is actually exact same method for the ideal gas law, same exact method for Poiseuille's law. Any of our equations can be ratioed like that. And I use that all the time in industry and real world things.
Is there a reason why for this one it's like direct proportionality, or like for for this one it's direct, but for the diffusion it was inverted, or like the inversion? R2 over R1 was the square root.
Let me see, where did I do that one?
No,
It was the same. Yeah, it was the same.
Wrong.
Okay. Did you get the 2s and 1s mixed? Yeah. Okay. Yeah. So it was time. It was straight across time. 2 and 2, 1 and 1. Great. Yeah. So notice how it's a different equation, but it's the same skill. That's what I'm trying to point out. And then I did a bunch of those with Poiseuille's law. So let's look at those. Before we do that, though, let's see. Benchmark value. Oh, yeah. Which benchmark value is inversely proportional to the square root of mass? And it's just having you look at that equation and see what the proportionality is. Now, do you see why it's all three? Because all three of those had the square root and had mass in the denominator on the other side. So they're inversely proportional to the square root of mass. Okay. And then this was just ranking them. We saw that the most probable was less than the average, and the average was less than the RMS. Okay. Now let's see. Rank the top. Rank from lowest temperature dependence to highest temperature dependence. Okay, so we're focusing on the temperature dependence, not the actual speeds. Okay, and so the temperature dependence is the same for all three. They're all proportional to the square root of temperature. If I were to say which is, rank them in terms of their velocities, then it would have been A. Most probable velocity is less than the average velocity, which is less than the RMS velocity. Okay. And so this is just the temperature dependence. What's the trick on number 18? Can you see how I'm being tricky on you guys? It's in Celsius, yeah. So it looks like you just doubled the temperature, but you did not double the temperature. You have to do all of these calculations in Kelvin. Yeah, so that's the trick. You got to convert to Kelvin. Okay. Let's see. Okay, so number 19 is a little tricky because most probable is equal to the square root of 2 RT over M, and you average, that was 8 over pi, right? And so what we have here is we've got an equation. Let's just take these two as is and and take the ratio here. And And so what cancels? Well, the R and the T cancel and the mass cancel. And we're left with these things. See, the 2 doesn't cancel with the 8 over pi. But now we have a relationship. We want to know what U average is, and we have UMP. So this number goes right there, and I've got the algebraic relationship because all of this stuff is gone. So I'm going to move the new average over to one side. Let's see. No, I'm going to, yeah. So I have new average is equal to new MP. And this 8 over pi is in the denominator. It's going to come up on top times 8 over pi. And this 2 is on top. It's going to move over to the other side and be on bottom over 2. So that's the algebra for getting from one to the other. Watch the video, go back and verify that my algebra works. So essentially I divided both sides by the square root of 2. It shows up down here. And I multiplied both sides by 8 over pi, and so it shows up over there. And then I multiplied both sides by a new average, and it's over here on the right. And then I just swapped sides. So those are about 4 steps. So we should expect it to be about 4 over 3.14 square root. So it should be close. So yeah, 352 moved up to 397. Here's another of the same kind of problems. There's nothing tricky about 21. It's just the smaller atoms have a smaller collision diameter. So helium has the least number of electrons, so it's a tiny little ball. So it's got the smallest collision diameter. So we have more of these same equations with the proportionalities. So let's look at the let's see, where is that equation? This one right here. So this right here is the volume in given time. So we could call that flow rate. And so let's write out all the proportionalities we can see. So F is proportional to R squared, R to the 4th power. F is proportional to 1 over the viscosity. F is proportional to delta P. Oh, that's okay. F is proportional to 1 over the length of the pipe. We'll just call this length. So we have all these. That's why I love this equation, because it's got so much business in it. We can, and there's and the R to the 4th. That's fantastic. So on the last video we talked about that. If you doubled the pipe, it would go up by 16. The flow rate would go up by 16.
So for the conflict question about the conductive thing, is it this? So for like number 10, so this helium, is it because it's smaller, so it diffuses faster, so the heat would?
It's because, okay, so it conducts, you're talking about conducting heat of helium versus argon or what have you. The thermal conductivity is proportional to the velocity of the gas. And so since helium is smaller, it has a higher velocity. So that's the connection. So let's see. if I have that. So here we go. Yeah, so here's the thermal flux is proportional to the pressure. So if you have a higher pressure of that gas, it's going to conduct heat better, right? So if we don't want any conductivity, if we want to make a good Yeti thermos, how do we get that thermal conductivity to go almost to zero? We get the pressure almost to zero. So they pull a vacuum inside that container. It's a double-walled container, and they pull a vacuum in between the walls. And so that's exactly what they're doing. They're insulating by pulling a vacuum and dropping that pressure. Okay, but if there is a gas in there, then it's going to be proportional to the velocity of the gas. So think about it, they're between two walls. So faster molecules can conduct heat faster. Whereas argon, a big old fat argon, is just going to barely go back and forth compared to helium. So argon is also really cheap. So our double pane windows have argon in between. So these are insulating windows. 90% sure they're insulating windows because that's like a. Yeah, you want to come look? Oh my.
Oh,
I broke it.
so not that one.
Yeah, not that one. Okay, look at that gap, that middle. This is a double pane window. And argon is.
Vacuum versus argon?
Well, see, it'd be really hard to pull a vacuum between those two panes of glass because you would have 14 pounds every square inch, or almost 15 pounds. And there's no way it could withstand that kind of pressure in the middle of the window. Okay, so they got to fill it with something. So they want to put a big, heavy molecular atom in there. And so about 1% of our atmosphere is argon. So that's pretty cheap. They can separate the gases, and they can concentrate argon. And so they put these double pane windows. They construct them, and then they pull it. I don't know. They can't pull a vacuum up to break the glass. So maybe they somehow they fill it with argon, and then they seal it up. And so this is an insulating window. Otherwise, all of our electricity costs in cooling the air would cause the go right out the windows. Because when glass is really dense, and so it's a great heat conductor. But yeah. So if you put a slow gas in between, it's going to insulate a lot better. And so density, conductivity, also the density of the material. There was a little table of things that I like to point to. Where is it? Here it is. Yeah. So where's glass? 1.2. Where's air? I don't see it, but oh yeah, up here, 0.025. So, so multiply that by 4 and you get 0.1. So 40. So glass is 40 times more conductive than air. Okay. So think about the temperature in the room. 40 times more heat would flow through the glass than through an air gap. Yeah, so that's crazy. And then if you could get vacuum, I mean, it's infinite, right? It just stops the heat flow from conductivity. So that's why the Yeti is so good. You can pull out all that air, and the thermal conductivity between those two walls goes to zero. Now, it's not exactly zero. This is thermal conductivity for collisional transfer of energy. There's also radiative. And so if you notice our glass dewars, they're double walled. So we pulled a vacuum, and then they're silvered so that light bounces off. So there's no radiative transfer. So we're trying to stop the radiation from going back and forth in the form of infrared. So any smooth surface will reflect infrared. So it just really has to be smooth for infrared, but for visible, they make it silvered. So the visible light bounces off, the infrared light bounces off the smooth surface. And so that's controlling heat. Making our windows out of diamond would be stupid, even if it was expensive, right? Like it's 800, and already just to get to one was 40 times, and so it's 800 times 40. Worse insulating than air. Right? So it's a lot. So diamond really does conduct heat. That's why we coat our tools in it. So the sharpness of a cutting tool is degraded if the tip heats up and melts, and it makes it a little dull thing. And so if you take a sharp cutting tool and you put a diamond coating on the surface, as it cuts, the heat runs down that coating and it wicks away the heat. And so as long as that tip of that tool is cool, it'll continue to cut. But as soon as that heat conduction stops, all it takes is that end of that tool to round a little bit. And now it's not cutting, it's chewing. And then it generates more heat, which causes it to round anymore. And this can happen in seconds. So like you're cutting a saw and it gets too hot, you're dulling the tip of that thing really badly. Yeah, right. And so it's mostly, yeah. Now, if you did have a diamond cutting tool, like a real diamond, like you could make, I guess, a diamond cutter. Like sometimes for glass, they have a little diamond tip and it just scratches the glass because it's harder. But most of it's just the heat conduction that they're trying to do. And they have like a really hard materials like silicon carbide that resist dulling. They're super hard and super high temp. So they combine the two. They'll have a carbide tip and a diamond coating, and that's a high dollar cutting tool or drill bit.
I know my dad bought like those diamond tip drill bits.
Yeah, that's right. Yeah, and they just take more abuse. They last longer. Yeah. And the concrete tools, my gosh, it's worth it because you'll sit there for 30 minutes. Or you sit there for 3 minutes. I mean, a good carbide tip, diamond cutting tool will just drill right into concrete. Yeah.
Trying to build a fence on a rocky hill.
Yeah.
We had the wrong tools.
Yeah. It takes forever. Yeah. So down here, which would be easier to separate, okay. Effusion through a pinhole, which is proportional to the velocity, root mean square velocity. So again, this is a combination because you want the lighter gases and the biggest difference. Okay, and so helium and hydrogen and oxygen are both fairly light, and they're a big difference. And that's going to be easier to separate than say two heavier atoms like maybe xenon and radon, or maybe even krypton and radon. They're both heavy, but they're going to effuse so slowly, so it's still going to be hard to separate them. But the lighter and the mass effect is more dramatic the smaller the number. Like the difference between 1/1 versus 1/5. Okay, that's going to be a bigger difference than say 1/5 and 1/10. Okay. Yeah.
When I was doing the math on it, it's like F2 and CL2 have like a slightly larger difference between their masses.
But because they're both heavier, yeah, there's not much difference between them in terms of their ratios. Yeah. Let's see.
But we're trying to have like a computational thermal flux problem, and on the homework. This was slide for it.
Oh, I just put those in there, like this one here.
Yeah.
I just put it in here in case I wanted to talk about it. Yeah. But yeah, just focus on the homework, and that way you guys can have confidence going into it. I really want you to do well.
It feels like a trick. I feel like I'm scared.
I know.
I feel like I understand it, but it has to be harder. Right?
I know. This is this part of the course should be the easiest because I'm just giving you a flavor for these transport things. Diffusion and viscosity, we hear about those terms all the time. And so they're in this course. It's really just like a quick dip the toe and let's have a test on it. Let's do well and boost our grades a little bit. And then
Okay, here's a graph. Hold this, and this.
Yeah, it was much more thinking involved in the last one. Yeah.
I covered like so much and nothing at all in the recast series.
Yeah, I know. it is just a little quick dip of the toe in the transport. There's a whole course taught on transport where you actually derive all of the diffusion coefficients and these transport properties. But it's an engineering course, and so I'm just giving you like a little kind of crash course section on transport. If you think about engineers, flow through pipes, heat management, diffusion of gases and whatever, for flow, like air, cooling air. I mean, we're cooling that air and flowing it in here. How many vents do you need? This would tell you, and if you have they leave the door open, how much diffuses out and in and so on. So the engineers are all over this stuff, and it's a hard course. There's a lot of math involved, and a lot of people, when they're in engineering and they get to transport, they have a real tough time. But maybe you love it, and maybe you want to just like bail on chemistry and do a master's in engineering. This would be the exciting part. Destiny is like, she's like, give me back to Friedel Crafts acylation.
That would just simply never happen. I don't know.
Yeah. I don't remember anything about Friedel Crafts, but I remember the names, like Arch and Crafts and Friedel Crafts. So, yeah, I'm not an organic chemist. So.
Yeah. Reminds me of Hans, also one that you should be confident in the spectrum. He got real mad when he asked what 2 times 6 was, and everyone was too scared to answer. He was like, "It's not a trick question." Are you sure it feels like a trick question?
I know. I don't know what's happened to y'all. I mean, it's like we ask an obvious question and nobody says anything. Like, well, I know the answer, but I'm not going to say anything.
Because when you're wrong enough, you start to just question even when you think you're right.
Is that it? I don't know what it is. I've always wondered. I taught the Boy Scout merit badge for chemistry. And these are 6th graders through sophomores. You ask any question and they're like, I want to talk. I want to tell you the answer. And then you get to college and it's like,
I feel like it really is the effect of the more you know, you don't know.
Yeah.
25 wrong about everything.
That's the, is that